Okay, I will be talking about, you can hear me? That's fine, great, okay. I'll be talking about the Korea Microenergy Grid Project, another I4 Energy project that really came out of a long-standing relationship between David Culler and one of his students who's now in Korea. Let's see, there we go. And so this is the overall outline. I'll talk about the objective, a little bit about demand response in California, and then talk about this building where this is really a living laboratory. I'll talk about that a little bit more. You can see the number of different companies that came together, both on the Korean side, Samsung, KETI, the Korea Electronics Technology Institute, as well as folks on campus like the Center for the Built Environment, and other companies like Slice Energy and AutoGrid, and especially the Software-Defined Buildings Group, of which David is a PI. So this really came out of the Korean ministry wanting to do demand response and wanting to learn about how we can use the infrastructure here that we've implemented at Satarjidai Hall with the BOSS system that David described and all the submetering that we have. And their problem is actually February evening peaks, a little bit different from the California story with respect to energy peaks. And they also were interested in creating a U.S. market for their products. And this is not a surprise to many of you, but this is the demand response slide. So basically looking at what's the problem here. And the problem really is peaks, that California uses 5% of capacity for less than 50 hours per year. So the idea really here is how do we reduce these peaks and improve both energy and the environment in doing so. And for California, it's summer afternoons where we see these peaks, primarily driven by air conditioning. This is one way of looking at demand response. As we were digging into this building and trying to figure out what strategies we would use, we realized that a lot of the things we were coming up with, we could use all the time on a daily basis, right? And so, but how do the strategies change as you change the unit of time? If you want to do something very quickly, what does that do with respect to what do you choose to use as your strategy? This is another way of looking at the type of automation you have versus the amount of information you have from sensors. So for this building, it's got an Apogee building automation system and a Watt stopper lighting control. This is up in the automation side. But we also want to encourage manual control. When do you start including people into the picture in terms of part of the actuation? They can also turn on and off lights, close windows. And as you get more and more information from sensors, as David was saying, whether it's CO2, light sensors, CO2 temperature, then you can actually either provide them better feedback, but also bring that up into the automation of the control and really close those feedback loops, demand control ventilation. Oops, excuse me. Oh, I'm sorry. So now I'm going to talk about the monitoring itself. So this building is still a relatively new building, 4 years old. The office portion of the building consists of a great deal of the square footage, 80,000 square foot, but the nanofabrication lab consumes most of the energy, about 75%. I mentioned the Siemens system. It has actually two chillers, a typical electric centrifugal chiller and a absorption chiller to use the campus steam. And the idea here was that you would use one system for the steam system during the summertime when we have plenty of steam, not used for heat, and use the centrifugal chiller the other times. It's a variable air volume system with reheat. And again, we've got this Watt stopper system. It's got tri-level dimming in the open plan offices and the occupancy sensors in the private offices. Citrus spent a lot of money and time in developing an infrastructure for submetering. The idea was that this would be a living laboratory, that we could actually run experiments on the building itself. So we have quite a few sense points in the building, over 7,000, recently upgraded to Ethernet. There was a campus-led monitoring-based commissioning project that did some commissioning as well as added these variable frequency drives on the water pumps, chilled water and condenser water pumps. The Distributed Intelligent Automated Demand Response project, this was a DOE project, funded project, our-based project that concluded last December. And this also added some more meters to the building as well as the idea with this project was the goal was to reduce 30% of the peak consumption. We were just looking at the office part of the building, so we needed to isolate the office from the rest of the building. This is just to give you an example of how much submetering is going on in the building. Each of these points is submetered. We added some new submeter points here. This is the one of the main substation A for the building. We also have B. This is each floor has both lighting and receptacle meters, so we can really drill down and see what's going on when we run our experiments. David showed this. I'm not going to go into it in detail, but the BOSS system that he described, the Building Operating System Services, really provided this infrastructure that we could actually go in and control the building and run these experiments. So we could, this describes what we needed to do for the KMEG project, which is we wanted to, AutoGrid provided this DROM system, Demand Response Optimization Management System, and we're able to connect this with the system through this SMAP driver to be able to read events, or I'm sorry, this is to push data, I believe, and this is our open ADR portion of the DROM system so that we could actually use the SMAP system to bring in those signals from the utility for demand response events. The submetering allows us to really look at the building and understand what's going on with the loads. I'm not going to go over in this detail, but it allows us to see things like this is an annual energy use summary, and we see that quite a bit of the building energy consumption is in the fabrication lab, both in the mechanical systems as well as the process tools. We started looking at the peaks of the building. Really, we need to understand what components make up these peaks, and so we know how best to address our demand response strategies. And so this is showing the peak load in Satarjadai Hall, and what the colored portion is the office plus a couple of loads that we are still looking to split out. We did that mathematically. But what we understand about the building is about, I said, about a quarter of the whole building load is in the office. And so what do we do with that? Like I mentioned before, we chose energy efficient strategies and demand response strategies. And so we were looking at increasing the supply air temperature of the building, increasing the zone temperatures. When we first came into this building, it had a single set point, 70 degrees, 24/7 year round, pretty much. And so we actually instituted a deadband. So we were able to increase the temperature range within the building. Reduce the ventilation rate. When we first surveyed the people in this building, they often complained they were cool. And this was all times of year. And this is Berkeley, where we have a mild climate. So the building was basically overcooled. Let's see, for daylighting, for the lighting system, we can turn off the lights and dim the lights. We have that control. As David mentioned, the interface that was provided to them, the web-based lighting control, really allowed us to better control over the lighting in general. In fact, just the implementation of that web-based control, I think, reduced the lighting consumption by about 50%. So we ran a number of events last October when we actually have hot weather in Berkeley, and we were able to shed on this is the air handling units. We were able to shed about 50%, 34 kilowatts, in our demand response day. We had a pre-cooling event that you see here. The lighting load, we were able to reduce by 46%, so 20 kilowatts or so. And let's see. If we ran about 3 events last year. We just happened to get a cool day, a hot day, and a warm day. Hot for us is about 95 degrees. That's pretty hot for Berkeley. Incidentally, this cool day was actually a demand response day for the rest of the state. So even though it was only 70, 75 degrees here in Berkeley, it was actually, it's still a good, sometimes you still need to have these demand response events, and we still need to show some sort of reduction. To be expected, it's a lot easier to shed load on a hot day because we're influencing the HVAC systems, which is the bulk of the load of the building. We were able to get to our 30% goal, or pretty close to it, for about 1 hour on the warm day. But I should say, all 3 days we were using the absorption chiller, and so the cool comes from steam. Had we been using the centrifugal chiller, the electric chiller, we would have actually achieved our 30% goal. So we were pretty pleased with the results of this. David actually mentioned this project, the demand control ventilation, when you bring in the calendar and the CO2 sensors. The idea here is how much deeper can you go if you have sensors distributed throughout the building. And so we had our KEDI team come in and install, it was about over 500 sensors, over 92 sensors. You can see them. I think there's one right here in the elevator lobby. And the sensors were temperature, light, relative humidity, passive infrared for motion, carbon dioxide. And we installed them in the private offices, conference rooms, and some of the corridors and around the open plan collaboratories on the 4th, 5th, 6th, and 7th floors. And the idea here is, what can you start doing once you have these sensors? We can do demand control ventilation, demand control temperature. We can start looking at light. We can also use these sensors to inform our demand response events. Sometimes we're sending signals out. We want to make sure that that control actually happened. We actually dim the lights in the place we wanted to. So this is an example of a sample installation. This is the 4th floor, and you can see the private offices have the sensors in the different locations. This is the open floor collaboratory, and we have sensors distributed throughout. We entered the metadata manually into the SMAP system. What this meant really was we wanted to associate each sensor with the VAV zone so that, again, we could correlate the temperature with that VAV. We wanted to know something about if there was a window, if the window was operable, what orientation it faced, what type of room it was, again, so that we could continue to refine these demand response strategies. Here's an example of a test that was run late May and in June. This was just on one floor where we looked at reducing the airflow, and then we can see the temperature and CO2 levels change based on that. There was also a survey done of the occupants at the same time so we can ensure comfort. So this is another way of viewing the data. This is through SMAP. Tyler Hoyt developed a very nice user interface where we could start looking at different zones and the air volume. So this is during the DR events. You can see the air volume decrease. And in some places, maybe there's more people there, and so that or it was a warm space, and so the air volume kicked in to make those people comfortable. You can see that the temperature rise, and we can see that we were getting up to 77, so still within our comfort zone. And you can see it really depends on the room. It's very individualized. And this is what we're interested in, is our power reduction. And you can see this is the supply fan power, and here's the submeter power for the whole, both air handling units for the office. So we were able to see a reduction there, but I think it was about 20 kilowatts. And again, as I mentioned, we also were interested in looking at the CO2 levels to make sure that when we do reduce the air ventilation rate, that we're maintaining a comfortable and productive environment for people. So we monitored that. So the next steps is we want to repackage the sensors to provide more secure installation for the public areas. We want to add labels to the sensors to inform people in the building what they are, what they're doing, how you can access this data. We've had a lot of interest from just the members of the community here in the building saying, hey, I want to know what's going on in my room, my space. We'd like to do more closed-loop DR testing so we can actually really drive down the temperatures, David's always calling me on this. We want to make a comfortable environment for the people, but we also want to save energy. And so trying to find the best balance using these sensors. And there we go. And we'll continue to administer the Center for the Built Environment's occupant survey in order to keep the place comfortable. So with that, I'll take any questions.